Good morning to all of you. Today we will do our next topic, which is the derivation of the wave equation in a string. So for this, let us consider a small portion of string. This will be the portion of the string, and T is the tension in the string. Let's suppose that on the one end, the tension is T, which is acting on the upward direction, and this is the tension in the second end, which is acting in the downward direction. And one more thing, we are assuming that the mass per unit length of this string is mu, and this lower one end of the tension is making an angle theta with the horizontal axis. Then second end is making an angle theta plus d theta with horizontal axis. And now we are considering that this string has a y coordinate is from the x-axis. It has a distance y, and we are considering that length of this string is delta x. Suppose one end is at x and then second is x plus delta x, so the length will be delta x. Okay, then we are considering that we are taking the y component of this force, which will we will equate this with the tension equations, force equation. We will draw that. So the motion in y direction, the force component in the y direction will be Fy. So Fy will be equal to, now this portion, this tension is acting on the downward direction and making an angle theta with this horizontal axis. So the component of this tension along this y-axis, or the y component, will be T sine theta. T sine theta will be the component of this tension along the y-axis. So this will be this. Now, because this tension is acting in the downward direction, we are taking it as a negative sign. Then second portion is making an angle sine theta. It is making an angle theta plus d theta with the horizontal, and the total angle, or we can say that this portion of this tension is making an angle with the vertical axis is 90 plus theta plus d theta. So we can say that it is the tension along this y-axis, or the force component along the y-axis, will be T cos theta, cos 90 plus theta plus d theta, means it will be T sine theta plus d theta. So this will be the force component along the y direction. Now we are assuming that if the length of this string delta x is approaching to 0, if the length of this string is approaching to 0, in that case, if this string length is approaching to 0, it means that delta x, this delta theta will approach to, uh, when we can say that if this delta x, if the delta x is approaching to 0, the correspondingly the angle, because it is going to this point is going to this point, it means that the angle, or we can say that this theta will be very small. So if it is very small, then we can replace sine theta is as a theta, and because this theta is going to very small, so correspondingly the cos theta will approach to 1. Now we are putting this equation, these conditions in this equation. We will get this y component of this will be sine theta is approaching to this theta, and so on. And from this equation, we will get this f of y component of the force will be equal to T into delta theta. Now here we are considering that the mass of this portion is delta m. Now according to Newton's second law, force will be equal to the product of the mass into the acceleration of by the system. Now the y component of this equation, or this Newton's second law, will be f of y is equal to delta m. We are considering this the mass of that string, this string. The mass of this string will be, we are considering delta m, so m is replaced by delta m. And acceleration, because here in this case the acceleration is in the y direction, is in the y components. We are considering the y components, so the acceleration will be the second derivative of y with respect to t. So from here we get two equation, or two equation of force. One is a y component of this force. One is Fy is equal to t and delta theta, and second one is f of y is equal to delta n into second derivative of y with respect to x. Now we will equate these equation. Their left hand side of these equations are equal, so right hand side should be equal. So from there we will equate this equation, and we will get this t delta theta is equal to delta n, the second derivative of y with respect to t. Now one thing we already discussed, because in this portion or in this article we are considering a small string. So mass of this, if we are considering, if we want to generalize this equation, so the mass will be varying with the length. If we are going a small portion, with a small portion the mass will be small, and if we are increasing the length, correspondingly the mass will be increased. So in this case, if we want to generalize this equation to from a small portion to a bigger area or bigger portion, then we have to replace this mass into some constant quantity. So here we are considering this mass per unit length, because mass per unit length will be constant whether we are considering a small portion of this string or the bigger portion. So we can generalize this equation to a high, from a small portion to bigger values or bigger string length. So in this case we are considering the delta m, we are replacing this delta m with the mass per unit length. Now this is the, if we are considering this is the small portion of the string, we are considering the mass of this portion is delta m and the length of this portion is delta x. So mass per unit length delta m by delta x should be equal to mu. We are considering this mass per unit length is mu. So from here delta m is equal to, we can equate, or we can move from delta x from here to this side. So we will get this delta m is equal to mu into delta x. Now we have to replace this delta m here with this equation. We'll get this equation, t delta theta is equal to mu delta x into second derivative of y with respect to t. Okay, now then we will rearrange this equation and we will get this delta theta by delta x is equal to mu by t into my second derivative of y with respect to t. Now from this equation, if we want to move this portion in this direction, we have to move this, or we can increase this to this one, and increasing this one this. So they will meet at some point, because this, now from here it is clear that there are the two parallel lines. One is this horizontal axis, this is this second horizontal axis. Now if the two horizontal axis is going straight line and one line is cutting these two lines, then the angle on one side of this angle should be equal to the angle on this side also. So from there we can say that this will be like a triangle. From here to like this, and with angle theta. And from here we can calculate the slope of this string. We want to calculate the slope of that string. So slope of the string will be equal to the tangent theta, because it is making an angle theta with the horizontal axis slope. So the tangent theta will be equal to change in y with respect to change in x. Now differentiating this equation, this tangent slope equation with respect to x, we will get this tangent theta is secant square theta into delta theta by d theta is equal to curly square by curly second derivative of y with respect to x. Now here we are changing this total differential operator into the partial differential operator, because from here that if we want to change total ordinary differential operator into the partial differential operator, there will be a term which is we are calling it as Poisson bracket. So the Poisson bracket should be 0 if we want to calculate if this ordinary differential equation will be equal to this one. So the Poisson bracket should be 0, and the Poisson bracket will be 0 in there will be two conditions. So one is that the energy of the system should be equal to constant. So if the energy of the system is constant, the correspondingly the Poisson bracket of that Hamiltonian or that energy operator with respect to y will be 0. Now we are considering here that it is a string. So in a string the energy will be equal, the Hamiltonian of the system will be representing the Hamiltonian of the system is representing the total energy of the system or a string. So the total energy will always remain conserved. So the Poisson bracket of y with respect to total energy of the system is 0. So we can replace the total ordinary differential operator into the partial differential operator. So from there we will get this equation. Now again we are assuming the conditions this. Yeah, if delta x is approaching to 0, then sine theta approaching to theta, and cos theta is approaching to 1. Now if cos theta is approaching to 1, then secant theta, that is 1 by cos theta, so that is also approaching to 1. So we can replace here secant square theta by 1. We will get this delta theta by delta x is equal to the second derivative of y with respect to x. Now one term is from here we get, and this one delta theta by delta x, the second derivative of y with respect to x, and one is this delta theta is by delta x is equal to mu by t into the second derivative of y with respect to t. Now the left hand side of these equations are equal. If the left hand sides are equal, the right side should be equal. We can replace like this. This is the resultant equation from this one, and by putting these or by equating these two equations, we will get this equation. Now from here, we can substitute that this T by mu. T is the tension. You can say that it is the force upon mu is the mass per unit length. So force means Newton upon Newton is if we want to generalize or we want to calculate, we want to know that what is this term. So we can convert this equation into the dimensional units. So from here this is the force and this is the mass per unit length. Then this is the formula for the or we can say that this is the dimensions of the velocity square of the velocity. So from here in this equation we can replace t by mu with v square, and this equation can be rewritten like this. The second derivative of y with respect to t is equal to v square into my second derivative of y with respect to x, and this is known as the wave equation for a string.